we still need to use the mic because of the people on Zoom, yeah? But we've turned it down slightly in the room to sort of help with the delay. So if you're asking a question at the back, can you please try to speak up a little bit? And I will try to do the same. So our next speaker is Florentin Daniel, who's going to tell us about stably stratified stars.
Okay, thank you. So good morning, everyone. For those of you who haven't talked to Florentin Daniel from Ecole Normale Supérieure, second-year PhD student, and I'd like to thank the organizers for giving me the opportunity to speak this morning. So my talk will roughly be divided into two parts. The first one concerns some work that was accomplished before I started my PhD by my two supervisors, Ludovic and C.Gissinger, as well as Florence, which is here, and which focuses on direct numerical simulations of what seems to be Dynamo of Tayler-Spruit. That has many similarities with theoretical predictions. And starting from that work, I will focus more on the subcritical nature of this Dynamo and try to show you how we've built a reduced model describing the main dynamics at hand. Okay, so a bit of context that we've already seen this week. So we're working on stably stratified zones of stars, that is to say, obviously zones which are stable. And from this very simple definitions, we are raising the first key thing we need to have in mind for this project is that we're going to need to find some source of motion in the star to generate and maintain the dynamo. And as we're going to see, a turbulent motion, because the dynamo that we're dealing with is indeed turbulent. So this is for the first thing, we need a source of motion, turbulent motion. And the second key aspect is going to be regarding the magnetic field role, and more particularly its implication towards angular momentum transport. So these are curves that you all know, but on the left, you've got the famous angular profile rotation within the sun. And you can see that if you've got some differential rotation, both with respect to the radius and latitude in the convective zone of the sun, as long as you move towards the radiative interior, you observe solid body rotation. And one of the possible candidates to account for this flat profile is that there is a magnetic field strong enough in this region, which is going to apply a magnetic torque in order to slow the star down. And this is what I want to illustrate here, a figure which we have seen before by Florence, I think I've shown it, where this team, again, Berger, have shown that if you conduct numerical simulation with or without magnetic field, you can indeed reproduce better the flat profile with the magnetic field in the radiative interior. Okay, so that's the second key aspect. It's going to be, besides the turbulent motion, it's going to be the role of the magnetic field regarding angular momentum. So one of the founding paper concerning dynamo action in the stably stratified interior of a star was proposed by Sprout in 2002. It's a very theoretical paper in which Sprout derived through analytical predictions a model for a dynamo to take place in this region. Lauren has already mentioned that on Tuesday. I'm going to quickly go back through that. So you all know the classical omega alpha dynamo loop. Here, the difference is going to be not on the first part, but on the closing of the loop here. So the first stage is going to use the omega effect of different phenomena like that, where you're going to end up with a toroidal field. But if this toroidal field has an amplitude which is going to be strong enough, it's going to be destabilized because of Taylor instability. And as it does so, it's going to regenerate poloidal motion, and it will allow the loop to be closed, and you can generate and maintain a dynamo in your system. Now, this is a very simple picture, very roughly summarized, but this paper actually has been discussed and criticized in the following years. And the main criticism came from Zan in 2007, who said that there was something missing in this process, because the toroidal fields that you would end up having at the end of the first stage of the loop would actually be axisymmetric. But the Taylor instability would introduce some non-axisymmetric motion. So non-axisymmetric field, background field would be axisymmetric, but the Taylor instability would bring up non-axisymmetric. And to go from axisymmetric field to non-axisymmetric, you would need something. And it's only recently that Fuller proposed to correct this discrepancy by introducing a magnetic cascade. And it's interesting to keep that in mind, because if the simulations that we have here rather go towards Sprout prediction, it's not a closed debate yet, and we should still keep in mind that some processes are not totally understood. Okay, so that's what theoretical part, and I've recalled just a few maths in his paper. So the idea that introducing the stratification frequencies, the Brun-Weisel here, and rotation, Sprout stated that the most unstable mode would be the m = 1. And that, thanks to that, he recalled the threshold for Taylor instability without or with thermal dissipation, as well as he was able to predict the level at which this field would saturate. And this is interesting to keep in mind, because this is something we can actually check in our simulations. All right, so that's for the theory. Now a quick word on our simulations. So we model the star as spherical quake problem in which the fluid is maintained in the envelope. But we're not interested in the interaction with the core that would be convective, for instance, in the star. So we're not going to let any flow evolve in there. We're just going to impose that the conductivity of the core is going to be the same, the one as the fluid. We're fixing the geometry, which is going to correspond to approximately a star of 3 solar mass. And we achieve stratification by applying a constant temperature gradient between the inner sphere and the outer one. And the molecular diffusion coefficients are maintained constant in space and time during one simulation. And as for the boundary condition, we've got no slip on both spheres. And what's important here is that we can actually vary the magnitude and the geometry of the field we're going to impose initially. And because we can test different scenario proposed in Sprout or in others. And last point, which is important, is that we impose the inner rotation at the inner core, and we maintain it during one entire simulation. Okay, so from that, the equations we solve are the classical MHD incompressible using Bussinesq approximation. And the solver we use is parody code, which was developed by Emmanuel during his PhD, and which has been added some optimization features recently by Julien Aubert and his collaborators. And the important parameters that actually are going to control the behavior of the system are the following. So we've got the Reynolds numbers. It's going to account for the level of differential rotation we're going to impose in the system. Got the Ekman number, which is here for the level of outer rotation, global rotation. And importantly here, we've got the ratio of Brun-Weisel frequency to overall rotation, which is here for the characterized stratification level. And finally, we've got the two ratios of molecular diffusivities. So I've shown some values that we can achieve numerically, which are obviously very far from what we can observe in real astrophysical objects, but we can still manage to observe some interesting phenomena spanning several decades and see whether they can extrapolate or not to a real system. Right, so now we've got all the ingredients to talk about the result, the important results. So this first figure from Ludovic, Florence, and Christophe's paper, in which that can be understood quite simply. So the idea is that you let your system evolve by implying a very weak magnetic field initially. It's going to be arbitrarily weak. And you see that bottom left here, that at the first stage that the magnetic field is going to go through is the first kinematic stage of increase. And if at the end of the first stage, the magnetic field is strong enough, in other words, if it's higher than this horizontal line here, it will become unstable and get a secondary amplification, which will make the field saturate at much higher level than if it had not crossed that line. What's interesting here is that this line here does correspond, is a very good agreement with the Taylor's local prediction for the threshold of instability. And the other important thing that's important to remember here, to understand here, sorry, that if you do not cross the line, you're going only to end up with a laminar dynamo. Whereas here, as Taylor instability sets in, you will have some turbulent motions and small scales will appear, which is what you can see on this 3D picture here. Small scales are close to the core and have appeared both for the hydrodynamical part and the magnetic field. And what we do concretely to control whether we're going to cross that line or not is by tuning the magnetic Prandtl number in order to change the overall Elsasser number, but not change too much the hydrodynamical state of the system, because I've not mentioned it here, but I'm going to talk about that in a minute. This is going to be very important to bring a first source of instability in the system. All right, so this secondary jump here can be seen more clearly maybe on this second figure, where on the top left corner, you also have the time series, but this time with physical units, where you see the secondary jump is going to appear for the magnetic field in red, and you've got the kinetic energy in black. But it can be interesting to see how the field behaves before Taylor instability here or after T1 and T2. For instance, for the dominant part of the magnetic field, the phi component, you can see here on this equatorial cut and here the meridional cut that you will have, so you are at the end of the kinematic stage of increase, so you do have a toroidal magnetic field. That's going to get a big amplification as it crosses Taylor's threshold. You can see 1 order of magnitude here. And what's important here, it's going to be important for me later, is that as it does so, small scales have appeared. I mentioned them before. They've appeared close to the core. It's going to be important for me to quantify the level of turbulence that is present in the system once the dynamo sets in. And so that's for the magnetic field. First thing I mentioned in introduction. The other part, which is concerning the angular momentum transport, can be seen here for the non-axisymmetric equatorial cut of the angular velocity. You also see these small scales that have appeared, but concerning what I introduced before with magnetic braking, you can see here the angular profile at the equator before Taylor and after Taylor, so in blue dashed before and in black line it's after. And you can see that as the Taylor instability sets in, this profile is going to be slightly flattened. Slightly because I recall that we impose the differential rotation here, and so the system has to reconnect somehow to the boundary. But this implication concerning angular momentum can be quantified properly, and it's been shown that you can actually measure the total torque and the magnetic torque that's going to be applied on the system. And it's been shown that the relevant scaling for the magnetic field in this system actually corresponds to Sprout's prediction from 2002. And the trick here is actually to compute Maxwell stress at the location where the magnetic field is the strongest. That is to say, at the equator.
So you don't have here temperature fluctuation. It's as a thermal or not?
We've split the temperature profile in a static one, which is not going to be here, but the buoyancy term is going to be due to temperature fluctuations here. Okay.
You do have distribution of potential energy related to the temperature.
What do you mean? Okay, maybe we don't do that later. Okay. Okay. Right. So that's for the part on transport. But what's going to interesting more now, which is going to interest me now, is going to be how the system behaves in this bifurcation diagram to move on to a more subcritical aspect. So what you see is the level of the dimensionless magnetic energy in the system as we fixed the outer rotation and the stratification, but as we change the level of differential rotation. And the picture here, which is here, is that if you start on the bottom left corner here, you're going to have a stable profile. So this is spherical quad problem, stably stratified layer. So you've got the cylinder here, which is going to be slightly curved because of the stratification, where you've got no non-axisymmetric motion. But as you increase the level of differential rotation, this Watson layer here is going to be destabilized at this point, will be approximately 0.35, and introduce the first non-axisymmetric motion in the system. And this is where you are here in this gray area, where you've got here this equatorial cut of the angular profile, the angular velocity, but here it's still laminar. And for this region here, if you increase again the level of differential rotation, you're going to end up purely hydrodynamical up to this point here, where you get this weak field that's going to develop first and gets the secondary jump that I was describing earlier. And as you do so, you actually get on this strong branch of magnetic field here, which interestingly has introduced turbulent motions at small scales. And you can actually maintain this magnetic field and the turbulence up to a level where the differential rotation is very low, is actually even lower than the first source of hydrodynamical instability that you would see in your system. And this is what interested me at first when I started my PhDs, was actually how to understand that better and try to identify the key ingredients to develop a reduced model. All right, first and last thing I need to mention that Ludovic insisted I mention here, that this system being subcritical here, what we did at first is that we imposed a weak magnetic field. But if you impose an initial magnetic field which is strong enough, you can obviously jump towards that branch here. And this is what I did here by imposing a strong dipole at first, which corresponds to the geometry Sprout's predicted. And if you do so, you actually jump toward the big branch that is here. And you skip the first kinematic stage of increase. And here you can see it with the symmetric part of the magnetic field and the antisymmetric part. The dipole is going to decrease as Tayler-Spruit developed here. All right, and now, so for the subcritical transition part, what I first got interested was this curve, as I talked about it, but more particularly in this the behavior of this point here. Because if we can indeed maintain turbulence and magnetic field at this low level, which is below this threshold of hydrodynamical instability, it was not so clear at first how this point behaved with respect to, for instance, the magnetic Prandtl number. So what I did is I retook this first curve here in black and used it as an initial condition to do the same kind of work but for different values of PM. And what you can see is that the higher the level of PM, that which is going toward the left here, the lower the differential rotation can be maintained up to level which are very low here. And this can be seen more clearly here as I track the points where I've lost the dynamo here with respect to the PM number. We've got this collapse of points here, which seems to correspond to the fact that the critical Raspy number is proportional to the inverse of the magnetic Prandtl number. Here I've just dropped one point here because I'm going towards a reduced model, which is going to work through close to the threshold of instability, and this point was actually a bit far and introduced a different hydrodynamical state. But for this curve here, so as I said, what seems to fit the best fits the data is that we're dealing with a critical Raspy number, which is proportional to the inverse of PM. In other words, having fixed the global rotation and the stratification, we have here a critical Reynolds number. And it's an interesting result because regarding Sprout's picture, this is actually compatible with what he predicted. He's got some prediction for this. It's come from his Q min, which is the minimum level of differential rotation needed to maintain its dynamo. And this actually, in other words, predicts a constant magnetic Reynolds number. Constant Reynolds number, which can be more clearly seen here as you plot the critical Reynolds number for the different values of PM with respect to the Raspy number, or Reynolds number here. And this is quite, I think, an interesting point to mention, because if you have in mind results from, for instance, Yannick Ponty or Shikoshin in the year 2000, the behavior of the critical Reynolds number with respect to the PM number would see first a linear increase and then a plateau. But here it seemed that we somehow have only a plateau as the the magnetic Reynolds number only changes by about 10%, around 7,000, 7,500, whereas the Raspy number changes by more than 1 order of magnitude. And if it's something I'd really like to discuss with you about, because it seems to be quite different from what Ponty or C.Gissinger found in the papers from before. Okay, so that's for the first thing I got interested in, and what I want to develop is so I said, subcritical transition to turbulence, but I still need to show that we've got indeed turbulence in the system, and I've not quantified that myself here yet. So what I did is that I probed the system, still having fixed every stratification and rotation. I probed the systems where the magnetic field was the strongest, that's to say at the equator, and I measured the fluctuation of the theta part of the velocity. Theta part because it was in our quad problem the one that we assumed would get the best with fluctuation at hand without any mean flow. And what seems to appear that once we do so and construct the same bifurcation diagram, that as we reduce the level of differential rotation here, it seems that the minimum level of fluctuations is maintained in the system, approximately 10 to the minus 3 in the unit of code. So this is interesting in terms of the fact that we are maintaining fluctuation at low level. This is still turbulent, but this turbulence here can be more clearly seen maybe on this inset, where I've measured the separation scale in terms of integral length scale ratio to a Kolmogorov microscale with respect to a Reynolds star based on this theta star. And you can see that all the MHD points here in colors do collapse on a curve which is proportional to Reynolds star to the 3/4, which corresponds to fully developed turbulence. Whereas the hydrodynamical unstable mode here do not go on that curve. So this means that we indeed maintain turbulence at this low level, and this seems that the subcriticality is controlled by this constant Reynolds number. And now I can actually move on to how we constructed the model, which seems to capture the dynamics at hand here by using only 3 modes. So I've insisted before on the fact that the main ingredient one of the main ingredients is going to be the dominant part of the magnetic field, which is the axisymmetric one. We've seen the cut where we've got a toroidal part, which is very strong at the equator, which is going to be the first mode I'm going to need here, which is going to correspond to T in my system. Then we also have a non-axisymmetric magnetic mode, which is going to play a role. At first, we thought about it as a Taylor mode, but it can be more than that. It's going to be really the non-axisymmetric mode that's going to help us close the system. And of course, this P mode, this magnetic mode, is going to be coupled with the rest with non-axisymmetric hydrodynamic mode, which is going to couple the rest. Think of the destabilization of the Stewardson layer. And if you look at the symmetries in the system, the model that we propose is the following, is that you've got these 3 coupled equations with these 3 modes. And the first in black, we've got the minimum ingredients for subcriticality, but what's interesting are the modes in the terms, which are in color here. I'm going to go through them quite rapidly. At first, all the coefficients are positive because this is going to be one point to make sure that we've got no axisymmetric dynamo possible. Non-axisymmetric dynamo, which is going to be also possible here by the VT term here in the second equation. But what I think is maybe the most important term is going to be more physical in the sense is this green term here, which if you couple to the first term minus nu p here, you see that if so beta 2 t square minus nu is positive, this p mode here is going to get an exponential increase. In other words, if I've written it here, if t squared is high enough, if your axisymmetric magnetic field is high enough, it's going to create an instability, a magnetic instability, think of Taylor instability, and get a developed non-axisymmetric motion. And finally, you've got obviously some induction term here, some EMF, which regeneration of the dominant part of the magnetic field through action of the flow and some non-linear saturation process due to some Lorentz force. Okay, and now that we've got this model, we can study it analytically, and we've got three very classical branches of solution: the trivial solution, the hydrodynamic modes that we've made sure are the only pure modes that are possible, and a non-zero solution of the system. And it's maybe more clear that once you vary lambda, so lambda, which is going to play the role of the Reynolds number in a system, differential rotation. And if you do so, you get the following diagram here. Here you can see that at first, the bottom left here, you've got no solution possible. You're stable on a hydrodynamical point of view, like in the white zone here for the DNS bifurcation. But if you get past this first barrier here, this lambda equal to 0, this is going to correspond to the destabilization of this 2 Watson layer. You're going to introduce the non-axisymmetric motions. This is the green curve here, this square root of lambda here. And at this second point here, a weak branch is going to appear, which actually, if it gets strong enough, is going to get this secondary jump I mentioned before. And you're finally going end up on that strong branch here, like in the DNS. And you do reproduce the bistability between the strong branch, S3, and V0 solution as before. And maybe the last thing I can show on this model here is what the behavior time series for two regions, for the weak magnetic field here and the strong branch here. For region of the weak branch, you see that in the DNS, both in the DNS and in the system on the right, the modes, which we've identified here, the one that corresponds the best in our simulations, they do not get past the threshold for Taylor instability as in the model here, and you do not get that secondary increase. Whereas if you get to the fifth region, if you get to the strong branch region, you see that in both cases, the toroidal magnetic field T is going to get past this line, and you're going to get this secondary jump I was describing before. So we do reproduce this this temporal evolution, but there are still things that could be done regarding that. Notably, for instance, maybe the noise of the system, because you see that for the DNS, some fluctuations appear once you get towards the branch that we do not seem to have here. So you could add, for instance, a stochastic process, but it's going to be a bit artificial in the sense that it's just going, if the amplitude of the white noise you add is not strong enough, you're going to simply add noise on this part here. So you could reproduce that. But you see here, we've built the model starting from the DNS of Taylor, but it could be actually maybe more general in the sense that we've got a strong, a large-scale magnetic field, so T in the system, but at some point it's going to be destabilized by some magnetic instability. Here it's Taylor, but in the case more general, it could be like maybe MRI or something like that. And as this magnetic instability develops, you get some smaller scale structures that appear. You've got the V modes and the P modes, and this modes, which corresponds to turbulence, end up close your loop. And in this sense, this system is actually, even if it started from the DNS of Tayler-Spruit, is actually more general, I think, in this sense, in the way that it captures really the picture that Steve was describing, I think, on Monday of non-linear dynamos. Okay, and to wrap up on that, so it seems that now Tayler-Spruit dynamo seems to be supported by DNS, but DNS that are still Boussinesque approximation, and we're trying to go towards a more realistic model, and we're working with people from CEA in France to go towards an elastic. And we've got this subcritical system, which seems to reproduce the main dynamics at hand, and that could be more general. And okay, and Christophe insisted that I would do some advertising for another PhD student who's trying to reproduce and observe Taylor instability in the lab. So Marlon Vernet at DNS, if you want, if you're interested. And of course, we'd like as well to do more link with observations. And I think this concludes my talk. Thank you.
Thank you, Florentin.
What is the source of turbulence here?
Okay, so it's really Taylor instability.
Okay.
Maybe.
In the beginning, you showed the time evolution of turbulent kinetic energy and magnetic energy.
Kinetic energy.
Yes, but also in such a system, there is a generation of temperature fluctuations.
Yes. Okay, yeah.
Yeah, which should be also included in the general energetic balance in order to analyze this.
Yes.
For example, I said, if you multiplied theta square fluctuations, if you divide theta square fluctuations by Brunt-Classic frequency in square, multiply by buoyancy parameter square, then you will obtain just potential energy in the system. And then there will be three energy: turbulent kinetic energy, potential energy, and magnetic energy.
Absolutely,
And
yes.
you can analyze
absolutely.
this system and it will be more clear.
Yeah, I think one of the reasons, maybe it's linked to your question here, that we're dealing here with a system which is stably stratified, okay, which is rather relatively slowly stably stratified, in the sense that it works up to n over omega, which is about 50. But the regime in which it was found is about n over omega to the order 1 or 5, if you want. So maybe that's why we dropped this, the part that you were talking about in the interpretation, but it does play a role, I think, at higher stratification.
If you multiply n square by the turbulent correlation time square, this parameter, it's a dimensionless number.
Yeah.
You can say, is it strongly stratified or weakly stratified? Just this product is just it's called turbulent Reynolds number or turbulent Richardson number.
Yeah. Okay.
Yeah.
Right. Right.
Okay.
Okay.
We
Yes.
can speak
Okay. We can
after
speak
that.
later about that. I guess what you mean. Okay.
Yeah. Nice talk. Thank you. Is it on? Okay. I talked louder. Okay. So you have two branches here, and you said the upper branch is the Taylor instability, so wave number 1. What is the lower branch?
Yeah.
It's also a dynamo, obviously. So what's happening there?
Yeah, and I think it's helping our system here. We've got this weak branch, absolutely. You could describe it as a hat dynamo, if you want.
What?
A hat-like dynamo that's going to develop, because, okay, here, the first thing we have is this non-axisymmetric motion, which is introduced as we destabilize the Stuartan layer, okay? And the mode that's going to be dominant of that is the m=1, which is going to be generating something close to the equator. And this is going to help this second branch, this weak branch that you're asking about, and which is going to be here. I don't think we can say more about that than this fact that it's laminar dynamo, which is helped by the m=1 generation of non-axisymmetric motions. And but it's in one sense helping the second dynamo develop. But yeah, apart from that, I can't do.
We need it for Zoom. Chris, could you pass it on?
Thank you for a nice talk. Yeah, about this branch. So you have two questions. First is following up on what was just asked. Do you see just the m=1 mode for the upper branch? And the second question is about the temporal evolution. Can you say in which, so you showed time steps in terms of time steps, code units, but can you say what is the equivalent in alpha and travel times or rotations?
Okay, so for the m=1, it's the dominant one. Okay, but the other one follows, but the m=1 is the highest stable. And also the time step. Here, no, that's okay. Here we've got it in the ohmic time. Okay, so we usually run the simulations for hours and ohmic time to make sure that we've reached the saturated state, and the one time step is dimensionalized by the inner rotation of the core. Okay, if it answers your question. So.
Yes, it does. Thank you. Maybe another question. Do you see and maybe I missed it, do you see the instability starting from the equator or from the poles?
No, actually, we see at the equator.
Thank you.
And I think this is related to your next question, is because we've got this first weak branch, which is present at the equator, which is helping the system. And this is setting the system at the equator, which is a bit weird with respect to the theoretical prediction, which make it more likely to happen at the pole. And this is one difference, I think, with the theoretical prediction between Sprout or Taylor or Hutchison and our results.
Thank you.
I take your point that if the Stewardson layer is unstable near the equator, then in the weak case, that makes sense that that's where you see the dynamo. But if you have the strong branch and then you reduce it into the subcritical regime where the Stewardson layer isn't unstable,
yeah,
then there's no reason why your dynamo should still be anywhere near the equator. Why does it not migrate to the poles then?
Well, that's a good question. I think this is related to the subcritical nature of the thing and the fact that at first he was here, that you maybe have no strong enough meridional circulation to make it go toward the pole, as you were thinking. But I know that, for instance, if you in a different regime here, this is very this thing here is very typical to the stratification level and the global rotation level we are at. But if we start the simulation at a different level of outer rotation and with a strong dipole, for instance, it seems that we are actually going towards more of the pole, as you were describing here. So I think this is very about the history of the dynamo branch that we're following. It seems that here it's not forgetting where it comes from in a way, and that's why it's not, I think, moving toward the pole.
If I could ask another quick question, does it matter whether your Raspy number is sort of positive or negative here?
We've only studied it for positive value. I think
Right, because you have m=1, you only get this for negative, which means the inner is slower.
No, the inner core is faster rotating than the outer core. But I think, yes, if you change the sign, it's going to change the regime. Yeah.
Yeah, but it wouldn't necessarily change the Taylor instability. That's kind of why I was wondering if you tried it. Not very helpful.
Thanks for the interesting talk. I was intrigued by your 3-mode model. I was wondering if you could do a quasi-linear analysis, or maybe like a generalized quasi-linear analysis to further make the connection between this sort of picture and what you're getting in the simulations.
Okay, I don't know about that, so maybe we can discuss about that later. But
Talk to Steve.
Okay, I'd be happy to. But yeah, what would be interesting, for instance, in this model, it's to find the critical magnetic Reynolds number, to find it back in the in this model. But it's not clear whether you should look at the evolution, for instance, of this point here with respect to nu or mu. I need to clearly identify which plays the role of RM or PM or whatever.
Any more questions? No, then let's thank Florentin again. And we just have an announcement before lunch.
Yeah. Yeah, I wanted to explain a little bit how we thought about running this program in the weeks in between workshops.